Okay, welcome to the first video that I'm making for Data Structures CSI 3334. My name is Greg Hammerly, and we are talking today about heaps. We're continuing with a discussion that we've already started in class about what a heap is. It's a type of priority queue. A priority queue is a data structure which stores a whole bunch of stuff and orders it by priority, not by, for example, the order in which it was inserted, or any other, or by uh, or by some other structure. Instead, the thing, and you can insert into a priority queue at any time, any value, but then the things will be ordered by the priority associated with each item. So each item has some priority value, which we call the key, and then that key determines in what order those things come out of the priority queue. So a heap is a particular type of priority queue. Um, the structure that we think of a heap as is a tree, as you see here, and it's like a binary tree in its most basic form. So every node has at most two children. We could have more children. We can build to heaps that are wider, but for now it's sufficient to talk about heaps with two children. I call this a semi-ordered data structure, as opposed to something like a binary search tree, which is totally ordered, so left is less, right is greater. Heap has the structure that higher priority items go towards the top of the heap, the top of the tree, towards the root, and lower priority items are buried deeper in the tree. And so we think of this as what I call the heap order property. And the heap order property is that the priority of the parent is greater than the priority of either of its children, or they could be equal. Now, it might look strange here that 3 has a higher priority than 5 and 3 has a higher priority than 8. That's because in this case, what we're talking about here is a min heap. A max heap has the opposite effect, where greater values are considered higher priority. But in our case, there are many times where we want a min heap. So things with lower values, lower keys, have higher priority. So we could think about this as if planes are landing at the airport and we want to prioritize planes coming into the airspace and when will they land, those with the lowest fuel might have the highest priority. So there you would want a min heap. So min and max heaps, they differ only by whether we consider larger or smaller keys to have higher priority. We've already talked a little bit about the structure as a tree in class. We've talked a little bit about the major operations that we want to support for a heap, and any heap must support at least these three operations. The three operations are to get the highest priority item, and since we have a tree, and since we have that the highest priority item is always above lower priority items, naturally the tree's root will have the highest priority. And so in order to get the highest priority item, which is one of the main operations, all we have to do is go to the root of that tree and we get it. And so we can do that in constant time. The second operation we want to perform or support is to be able to insert any item and with some key. And we want to be able to do this in log n time. The way we do this is in 3 steps. The 3 steps are, first, to find the highest leftmost null pointer. And you'll see here I have written that you can do this in order 1 time, in constant time, using what I like to call magic. And we'll explain what magic is at a later point in the discussion. But for now, let's assume that we can find the highest, when I say highest, I mean highest in the tree, leftmost null pointer. And in this case, for this example, that would be this right here. That's a null pointer. And let's say we wanted to insert the value 10. 10 goes there. We create and attach the new node, which we can do in constant time by creating the node and fixing that pointer of the parent to point to it. And then the third step is, if there's any violation of the heap order property, that is, that the parent should have higher priority or equal priority to its children, then we need to fix that. And we can fix that by doing what we call bubbling up of the new node. So the new node is here. Do we want to fix its priority or its position relative to its parent? Well, in this case, no. Its parent has a higher priority, so it's fine. Let's go ahead and do that again. Let's do another insert. So if we insert something, where's it going to go? Well, it's going to go in the highest leftmost null pointer, which is this. How do we find that? Again, by magic. We'll talk more about how to find that later. And let's suppose that we insert the value 5, or let's take 6 as an example. So we take 6. When we take 6, we put it there. Now we have a violation of the heap order property, but we can fix that violation by, again, bubbling up from 6, and we compare it with its parent. They're out of order, so we can swap their two values and do one bubble. So 6 goes here, and 8 goes here. And just by swapping them, we fixed the problem between those two nodes, but we have to continue on up the heap and say, is 6 out of order with respect to its new parent, which is 3? Well, in this case, no, so we're fine. We don't have to go any further. So our bubble up operation started here, ended here. Let's insert another node, say value 2. Again, it's going to go to the highest leftmost null pointer, which is this, and we create the node here. It has a heap order property violation with its parent, so we're going to bubble up at 2 and swap 6 and 2. Now we continue on up the heap and we compare 2 with its parent of 3. And again, there's a heap order property violation, so we swap those two. Once we've gone all the way up to the root, we can't go any further up the heap, so we're done. And you'll notice now that the heap is completely in order, according to the heap order property. Okay, so we can insert an item, any item, in log n time. The reason it's log n time, well, we can find the highest leftmost pointer, null pointer in constant time using some unknown magic. We can create and attach the node in constant time. So the number of operations that we have to do to get from possibly the bottom of the heap all the way up to the top is possibly log n, because we have log n layers of this heap because it's an extremely balanced data structure. Now, the reason it's balanced, we haven't talked about this yet, is the fact that we fill the heap in left to right, or top to bottom, left to right. And we do this when we're looking for the highest leftmost null pointer. So we would fill in first the root, then this node, this, there, and then we would continue on like this, right? And these are the places where we would position new nodes. And because of that, the heap always maintains this structure that is very balanced, where from any node, the number of children to the left and to the right of that node are approximately equal. And so the number of layers that we have in this tree is approximately log n at all times. Let's talk then about removing. We can remove only the highest priority item in log n time. Heaps do not support efficient removal of any other item, only the highest priority item, which in this case is the root. So the way we do this is a bit counterintuitive. Again, the first thing that we do, well, you might think that you could just erase the root and then you get a gap in there and then you could fill in that gap by moving up one of its children. The problem with that is the issue of balance. If you do that, and try this yourself, if you do that and you do that over and over again, you're going to end up with a heap that becomes imbalanced over time. So what we're going to want to do is we're going to actually want to replace the root node, which is going away anyway, with the last used position where we made an insertion into the tree. Not the value itself, but the position. So that's the lowest rightmost non-null node. In this case, it's 6. So we'll take the 6 out of the tree, or out of the heap, and we'll place it at the root. Now this seems like a silly thing to do, because we're moving something with low priority up to the highest priority, which is bound to, in many cases, cause a heap order property violation. But we can fix that by doing what we call bubbling down, starting from the root. So we compare 6 with its 2 children. Clearly we need to make a fix here because 6 is, 5 has higher priority than 6, and 3 has higher priority than 6. Well, we can do this by comparing 5 and 3, and clearly we want the lesser of those 2 nodes to be the replacement for 6, because if we took not the lesser, if we took 5, for example, then and we replaced 5 and switched 5 and 6, we would then have a heap order property violation between 5 and 3. So we take 5 and 3, we take the lesser of those 2, which is 3, we compare it with 6, we determine that we do need to swap, and so we do that swap. So 3 comes up, 6 goes down. Now we need to continue our bubble down at 6. We compare it with the lesser of its 2 children, or its 1 child in this case, which is 8. There's no violation there, so we're done. Okay, let's do one more remove. If we're going to remove, what are we removing? Of course, the least item in the tree, the highest priority item in the tree, which is 3. And how are we going to do it? We're going to replace it with the lowest rightmost object in the heap, which is 8, this 8. When we do that, we take 8, we promote it up to the root, and we bubble down, starting at the root, and we say, of its 2 children, 5 and 6, the least is 5. So we're going to compare 8 and 5. There's a violation of the heap order property there. So we swap 5 and 8. And we continue bubbling down. Now in this case, we don't have to go any further, because if we look at 8 here, and we compare it to the lesser of its 2 children, those have equal priority. We don't have to make any further swaps, because a parent can have equal priority to its child. So again, if we believe that we can find the lowest rightmost node, which currently is 10, in constant time using what I'm calling magic, then the remaining work is log n, because we move that node up to the root and we bubble down, and we may have to go all the way back down to the bottom, which is again log n steps. Each of those bubble down steps, just like each of the bubble up steps that we talked about for insert, cost constant time, and they're log n levels of the tree, so log n time. Next time, we'll talk about how do we get this magic so that we can identify where the places to insert and remove are.